In a chemical reaction, you have what's called the reactants on the left and the products on the right. And the reactants and the products are separated by an arrow in the middle. And this is how we denote chemical reactions. In order for a reaction to occur, those bonds between the reactants must break, and that requires energy to then make the products. There's also something called enthalpy, which is heat energy. The change in enthalpy is the energy difference between the products and the reactants of a chemical reaction. When the enthalpy of the reactants is higher than the enthalpy of products, then energy is released, and therefore the change in enthalpy, delta H, is said to be negative. These types of processes are called endothermic reactions, where energy is a product. In endothermic reactions, the opposite is true, where the reactants have a lower enthalpy than the products, and energy is absorbed. So we say that the change in enthalpy is positive, or delta H is positive, and energy is a reactant. Here are some examples of endothermic and exothermic reactions. Kilocal is a unit of energy, and so is kilojoule. Pause the video and think about which one is exothermic and which one is endothermic. In the first reaction, you have a delta H, or change in enthalpy, of negative 16 kilocals. That means that energy was released. So therefore, the reaction is exothermic. In the second reaction, it says here that 73.7 kilojoules is in the products. So because the energy is in the product side, then the reaction is exothermic. Chemistry of an ice pack. So an ice pack gets colder when it's cracked. So what does that mean? Why is it cold? The reason why it's cold is because energy is being absorbed from your hands to the ice pack, and that's why it feels cold. Therefore, this process is endothermic. We can also measure the conversion of reactants to products over time, and this is called kinetics, or the rate of a reaction. So here we have a reaction A goes to B, where each red sphere is A and each white sphere is B. And as you see, to start, there's completely all reactants. And over time, the reactants begin to convert to products. We can see here, where there's a plot of number of molecules per time, that the concentration of the reactants decreases as the concentration of the products increase. In a chemical reaction, energy is required to break the bonds of the reactants in order to make bonds of product. In this class, we're only going to talk about the rearrangement of atoms in a reaction, but note that there are reactions where there's only an exchange of electrons. But we're not going to get into that here. Can you tell me whether this is exothermic or endothermic? Here, your change of enthalpy is negative, so therefore energy is released, and therefore this is an exothermic reaction. So in a chemical reaction, the reactants go through what's called an intermediate stage, or here, an activated complex, in order to get to the reactants. In order to form that intermediate, enough energy is required to form it. And that minimum amount of energy is what we call the activation energy, or E sub A. In this energy level diagram here, it's an exothermic reaction, and we know that because the difference in energy between the reactants and the products is negative. And negative change in enthalpy means that energy has been released. Think about how you would draw an endothermic curve. So here we have an exothermic curve. Take a second to draw what an endothermic reaction would look like. Keep in mind that the activation energy is always going to be positive. Pause the video and draw what you think endothermic process would look like. Remember that an endothermic process means that the reactants are lower in energy than that of the products. So the change in enthalpy is positive because it's absorbing heat, and there is a positive activation energy. So the hump goes up, not down. So what are some things that may affect reaction rates? The structure of the reactants is important. If the reactants have opposite charges, then they will react more. This is more true when the ions are disassociated. Ions of the same charge will not react. And also the bond strength between the atoms plays a role. The magnitude of the activation energy is proportional to the bond strength between atoms. Now the orientation or the shape of the molecules will also play a part. Let's consider this reaction here, where one element A added to a compound B, C forms A, B, and C. So here I have A and here I have B, C. Notice that currently the way they are aligned. So if they hit each other, then a reaction will form. If they collide at a slightly off angle, then they will not react. It has to be at a certain orientation for them to react. And notice how in this case they didn't hit very hard, right? So it doesn't have enough energy in order to overcome that activation energy. So even though they're hitting dead on, that activation energy must be met. So if I raise the temperature, then the reaction will occur. You can imagine the concentration of the reactants also matters, because you have a higher chance of particles meeting at the right angle. So here we have a couple and nothing's really reacting. And there's two things here. Number one, the energy hasn't been fulfilled. So we have to increase the energy so we can overcome that activation energy. So if I increase the concentration of the reactants, if I increase the concentration, then the probability of the reactants colliding at the right orientation is higher. So if you notice, there's one of the products right there, and here's the other one. If I increase the temperature, meaning energy, then I can overcome that activation energy required to make the products. So if I raise temperature, so that it's above the activation energy, then there's a higher probability of the reactants hitting at the right orientation. Now the physical state of the matter also makes a difference when the reactions are happening. So remember that solids are closer together and they only vibrate slightly, where in a gas state they're often very far apart. So in order for the reactants to collide, it's of a lower probability. But in the liquid state, they're still close to each other, but they're allowed to move freely, and this allows for higher probability of the molecules colliding and forming the products. So the reactions go faster in liquid state and relatively slower in the gas and solid state. Now you've probably heard of a catalyst. And a catalyst increases the rate of reaction, but it is not used up and it's not part of the reaction. And so it does not alter the final product. It just allows for the reactants to undergo a different path to get to the products, and it reduces the activation energy. So as you can see here, we have the reactants, the activation energy, and here are the products. Where in the presence of a catalyst, notice how the energy of the reactants is the same and the energy of the products is the same, but the activation energy is lower. And this is because the catalyst forms a different intermediate state than if it was not present. Let's take elephant's toothpaste as an example.